Story 1. The Antikythera Mechanism, Greece, 100 BC. In 1901, sponge divers working the Aegean seabed off Antikythera surfaced with something wrong. Not statues. Not coins. A corroded mass of bronze fragments fused into stone. It was catalogued as debris. Then someone noticed teeth. Gear teeth. From a Hellenistic shipwreck dated with certainty to the 1st century BCE. It shouldn't have gears. Not this early. Not this precise. The fragments were boxed, labeled, and shelved in the National Archaeological Museum of Athens. For decades, they gathered dust. No announcement. No urgency. Just an object that didn't fit. When researchers finally examined the fragments seriously, the problem became unavoidable. Inside the corrosion were interlocking bronze gears, over 30 of them, with triangular teeth cut to consistent angles. X-ray and later CT scans revealed differential gearing capable of modeling complex astronomical cycles, lunar phases, eclipses, planetary motions. This was not a clock. It was a predictive machine. The inscriptions, faint, technical, instructional, described cycles in years and months with mathematical confidence. The gear ratios matched known celestial period with errors measured in fractions of a degree. The math was right. The dates were wrong. The timeline broke. Nothing like this was known to exist for another 1,400 years. The response was cautious to the point of paralysis. Early reports softened language. Analog calculator replaced machine. Public displays minimized function. For much of the 20th century, only a handful of specialists had access to fragments. When advanced imaging was proposed, funding stalled. When results came back too clean, interpretation slowed. No claims were falsified, but few were amplified. The scans disagreed with history. So history didn't move. No workshop was identified. No tooling survived. No clear technological lineage followed. One of the early investigators, physicist Derek de Sola Price, spent decades defending the mechanism's sophistication. His conclusions were contested, then partially accepted, then quietly absorbed without consequence. He died before modern CT scans fully validated his most controversial claims. He never saw the full reconstruction. Meanwhile, the device remained framed as an outlier, brilliant, accidental, singular. The implication that advanced mechanical engineering existed, was taught, and then vanished, was left unexplored. Because if it wasn't singular, the damage would spread. In 2005, high-resolution CT scans recalibrated every gear, forcing a second look. Story 2, Roman concrete Mediterranean basin, 200 BCE, 100 CE. The structures were never meant to survive this long. Harbors, seawalls, domes, exposed to salt water, storms, and seismic stress should have failed within centuries. Instead, many Roman concrete structures are still standing after 2,000 years, while modern equivalents crumble in decades. The water made it stronger. That was the first problem. Archaeologists initially assumed durability was a coincidence of mass. Engineers disagreed. When cores were extracted from ancient piers submerged since the Roman Republic, they revealed something no modern mix should show: internal growth. The concrete had evolved after setting. Laboratory analysis identified a volcanic ash binder, pozzolana, combined with lime and seawater. But that alone didn't explain the strength. Under electron microscopes, researchers found bright white inclusions once dismissed as sloppy mixing. They weren't mistakes. These inclusions, lime class, were reacting with seawater over time, triggering crystalline formations that seal cracks as they formed. Self-healing concrete. Not metaphorically. Chemically. Not impurities. Intentional design. Delayed reaction engineering. The Romans had created a material that anticipated failure and corrected it. What's missing is how they knew. No surviving technical manuals describe the process. Vitruvius writes about ingredients, not proportions or thermal control. There are no transitional experiments, no records of failed batches. The knowledge appears fully formed, deployed at scale across an empire, then disappears. As Roman infrastructure collapsed, so did the recipe. Medieval builders reused Roman concrete without understanding it. Renaissance engineers admired it without replicating it. By the time modern cement emerged, the ancient method was gone. Access narrowed quietly. Early 20th century studies that questioned the impurity explanation were sidelined. Later papers softened conclusions, emphasizing environmental luck over human design. Funding prioritized modern materials. The ancient formula remained academically interesting, but operationally ignored. One Italian materials scientist spent years advocating for deeper replication trials using ancient methods. His grant expired. The project dissolved. He returned to commercial cement research. He never finished the tests. Only in the 21st century did high-resolution spectroscopy force a revision. Heat mixing techniques were identified. The lime class weren't accidental. They were the result of hot mixing, a dangerous process producing unstable quicklime, inclusions that later activated underwater. This wasn't primitive construction. It was controlled risk engineering. And it raises a question the field still avoids. If Roman builders understood long-term chemical behavior this precisely, what else did they optimize that left no paper trail? Because once the empire fell, the method wasn't preserved. It wasn't simplified. It wasn't improved. It was forgotten. Modern engineers are now racing to reverse engineer a process already proven across millennia. Patents are filed. Replication begins. The ancient solution returns, rebranded. But the original context is gone. The training system vanished. The reasoning behind the design choices is still inferred, not known, and the sea kept the proof intact. Harbor cores dated across 2,000 continuous years. Story 3. The Baghdad Battery, Mesopotamia, 200 BC. It was found in storage, not in the ground. In the 1930s, while cataloging artifacts near Baghdad, a German archaeologist pulled a small clay jar from a crate marked miscellaneous. Inside it was a rolled copper cylinder. At its center, an iron rod, sealed with asphalt. No decoration. No inscription. No explanation. It looked wrong. Too deliberate. Too contained. At first, it was dismissed as a scroll holder. Then someone noticed the ceiling. The asphalt wasn't ornamental. It was insulating. And when replicas were assembled and filled with acidic liquid, wine vinegar, grape juice, the result was immediate. A measurable electric current, low voltage, stable output, repeatable. In controlled tests, the device produced roughly 1 volt. Not a shock weapon, not lightning, but enough to plate metal, stimulate chemical reactions, or demonstrate electrochemical principles centuries before they were supposed to exist. This was not theoretical electricity. It was functional. Skeptics argued coincidence. Ritual object. Storage vessel. But the geometry resisted those explanations. The copper and iron were deliberately isolated. The seal prevented leakage. The materials were chosen, not accidental. The configuration mattered. The chemistry worked. The effect was real. What's missing is context. No wires were found. No workshop. No diagrams. But ancient texts from the region describe gilding techniques that modern chemists recognize as electroplating. Thin, uniform metal layers that fire gilding alone struggles to achieve. The method appears. The artifact exists. The explanation vanishes. When the object enters museum circulation, its label changed. Possible galvanic cell became ceremonial vessel. Requests for expanded testing were deferred. Replication studies were conducted quietly, then filed without follow-up. The current didn't fit the story. During the mid-20th century, one researcher attempted to trace similar jars across regional collections. He found several candidates. Then access tightened. Storage locations changed. Correspondence stopped. He missed his daughter's graduation. The trip was canceled. The funding didn't renew. By the time public interest revived decades later, the object had been neutralized by framing. A curiosity. A footnote. Something that could be but likely wasn't. Yet no alternative explanation accounts for all components working together. Remove one element, the copper, the iron, the seal, and the effect disappears. Leave them as found, and electricity emerges. Not as myth, as measurement. The larger implication is not that ancient people powered cities. It's more precise and more uncomfortable. That they understood principles they did not formalize in surviving texts. That applied knowledge existed without theory. That experimentation may have been localized, taught orally, then erased by conquest and time. Because once the region destabilized, the practice didn't evolve. It didn't spread. It ended. Modern demonstrations now reproduce the effect for students. 1 volt. Sometimes more, with series connections. Enough to prove intent. And enough to raise the same question again. How many other functional technologies were mislabeled because their outcomes arrived too early? Replication voltage logged at 1 volts. Story 5. Egyptian stone machining, Giza Plateau. Old Kingdom, 2600 BC. The cuts are the first warning. Granite boxes. Basalt sarcophagi. Core-drilled stone samples pulled from bedrock near the pyramids, each bearing marks that shouldn't exist at this date. Smooth walls. Uniform channels. Spiral striations that suggest continuous rotation under controlled pressure. Stone doesn't behave like this. Not with copper. Not with sand alone. Early Egyptologists described the craftsmanship as astonishing. Later engineers used a different word, inconsistent. The feed rates implied by the drill marks, how fast the tool advanced through granite, exceed what hand-powered copper tools should achieve by an order of magnitude. Microscopic analysis revealed parallel tool marks with constant spacing. No chatter. No slips. No irregular stops. Whatever cut the stone moved steadily, under load, without hesitation. The motion was controlled. The pressure was constant. The result was repeatable. These were not ceremonial cuts. They were industrial. When modern machinists attempted replication, using reconstructed copper drills and abrasive slurries, the results fell short. Cuts wandered. Surfaces tore. Tools were accelerated. To match the ancient marks, something else was required, either harder tooling, higher rotational speed, or a method not preserved. No such tools have been recovered. That absence became the explanation. The prevailing narrative reframed the precision as symbolic. Ritual importance justified effort. Time replaced technique. If it took long enough, anything was possible. But time doesn't create uniformity. Skill doesn't erase vibration. Patience doesn't generate torque. During the late 20th century, several engineers published measurements quantifying the tool marks. The conclusions were uncomfortable. The papers circulated briefly, then stopped being cited. Access to certain artifacts tightened. Requests for additional sampling were denied on preservation grounds. The data stalled. One independent researcher spent years measuring drill cores stored in museum basements. His findings never reached a major journal. Funding evaporated. He sold his equipment to pay legal fees tied to access disputes. He never returned to the plateau. A fair counterargument exists. Unknown abrasive compounds or lost stoneworking techniques could, in theory, account for the marks without advanced machinery. That explanation remains possible, but unproven. What is proven is this: the surfaces exist, the measurements hold, and the methods described in surviving texts do not account for the results. If Egyptian stoneworkers possess a mechanical process later civilizations failed to inherit, then this wasn't just architectural genius. It was a manufacturing capability that appeared fully formed, was used extensively, and then vanished. No transitional phase. No documented decline. Just silence carved into stone. Modern scanning continues. Laser profilometry confirms what calipers suggested decades ago. The tolerances are real. The question remains operational. Because if these cuts were intentional, and the evidence says they were, then ancient Egypt wasn't just building monuments. It was machining them. Micron-level tool paths measured across multiple core samples. Story 6, the Delhi Iron Pillar, India. 400 CE. It stands exposed to sun, rain, and monsoon air in the heart of Delhi. No shelter, no coating, no modern maintenance. And yet, after more than 16 centuries, the iron shows almost no corrosion. This should be impossible. Pure iron rusts aggressively in humid environments. Even modern steel alloys require protective treatments to survive decades outdoors. The Delhi Iron Pillar has endured longer than many civilizations, without flaking, without structural loss, without explanation. The surface is intact. The core is sound. The rust never arrived. Early visitors assumed divine protection. Later scholars suggested climate. Both explanations failed under testing. Metallurgical analysis revealed a composition unlike modern wrought iron, high phosphorus content, minimal sulfur and manganese, and a slag structure that encouraged the formation of a thin, stable protective film. This passive layer, microns thick, forms naturally and then stops further corrosion. Not paint, not plating. A self-limiting chemical shield. The process requires precise control during smelting and forging. Temperature, oxygen exposure, cooling rate. Get one variable wrong, and the effect disappears. This was not luck. It was process. Repeated successfully. The pillar weighs over 6 tons. It was forged in sections, forged welded, and erected without cracking. No modern corrosion inhibitors. No stainless alloying. Just iron, engineered to last. What's missing is the method. Ancient Indian texts describe iron production, but not this outcome. No recipe explains the phosphorus enrichment. No manual details the environmental controls required. The knowledge appears in the object, not in writing. As centuries passed, the technique was lost. Later Indian ironworks produced excellent steel, but not this. By the medieval period, the pillar's resistance was already mysterious. Understanding regressed. In the 20th century, repeated studies confirmed the anomaly. Each paper explained the chemistry, but stopped short of addressing how ancient smiths consistently achieved it. The pillar was reframed as a fortunate convergence of materials and environment. Replication attempts struggled. One metallurgist involved in early corrosion studies spent years trying to recreate the passive layer in control furnaces. He came close. Then funding shifted to modern alloy research. He died before publishing his final results. The implication is quiet but sharp. This was not an isolated experiment. It was scalable. It was repeatable. And it was taught well enough to produce a 6-ton monument that resists time itself. If this level of metallurgical control existed in the early first millennium, then the technological baseline of the era has been misjudged. Because the pillar doesn't argue. It doesn't corrode. It simply remains. And with every passing year it survives. The gap between what ancient engineers did and what history says they could do widens. 16 centuries. No rust. Story 7. Inca polygonal masonry, Andes Mountains. Pre-Columbian era. The stones don't line up the way they should. There is no grid. No symmetry. No repeated block size. Instead, massive polygonal stones interlock like fractured glass, each face uniquely shaped. Each joint fitted so tightly a blade cannot pass between them. No mortar. No filler. No margin for error. These walls have survived earthquakes that flattened colonial cities built directly on top of them. When the ground moves, the stones shift slightly, then settle back into place. Energy is absorbed, not resisted. The wall moves. The wall survives. Early Spanish chroniclers were baffled. They described the masonry as impossible without iron tools. The Inca had none. No steel chisels. No wheeled transport. No draft animals capable of hauling multi-ton blocks up mountain slopes. Yet the stones are real. Some weigh over 100 tons. Many are andesite and diorite, hard volcanic rock resistant to fracture. The contact surfaces are not flat. They are subtly curved, allowing rotation under stress. This was not brute stacking. It was structural design. Modern engineers studying seismic resilience recognize the principles immediately: load distribution, stress redirection, dynamic response. But these concepts are embedded physically, not mathematically. The walls are the blueprint. What's missing, again, is the method. Quarries have been identified, but tool marks are scarce. Transport routes are debated. Experimental archaeology has moved stones, but not with the same precision. Shaping a single face can take months using replicated stone tools. The Inca did this thousands of times. Consistency is the anomaly. When academic narratives addressed the problem, the solution was reframing. The work was labeled symbolic. Time and labor replaced technique. Precision became patience. But patience doesn't explain curvature. Labor doesn't explain repeatability. Symbolism doesn't explain seismic performance. During the mid-20th century, several Andean engineers proposed that the Inca used a systematic fitting process, iterative shaping guided by physical testing, not measurement. Their work received little traction outside regional journals. One of them left academia entirely. He returned to his village. The research stopped. The walls remain. They show no learning curve. Early constructions are as precise as later ones. There is no gradual improvement. The knowledge appears mature from the start. And when the Spanish disrupted Inca society, the technique did not survive. Colonial buildings cracked and fell. The older walls held. Today, restoration teams avoid dismantling the masonry. Once a stone is removed, it is nearly impossible to return it to its exact position, which means the process was not only advanced, it was irreversible. If this was engineering, it was engineering without drawings. If it was science without notation. A physical intelligence, encoded in stone. And one more reminder that some technologies don't fail. They're simply abandoned. Joint counts exceeding 12 faces per stone, measured across sites. Story 8, Greek fire, Byzantine Empire, 7th century CE. It burned on water. That single property altered naval warfare for centuries. When Byzantine ships released Greek fire, enemy fleets didn't sink, they ignited. Flames crawled across waves, clung to hulls, and resisted every known method of extinguishing. Water fed it. Wind spread it. Panic finished the rest. Contemporary accounts agree on the effect, even when they disagree on everything else. Arab, Latin, and Greek sources describe the same terror. A weapon that behaved unlike fire and could not be escaped once deployed. This was not a crude incendiary. It was a controlled system, stored, pressurized, and projected through siphons mounted on ships. The delivery mechanism alone required metallurgical precision and pressure management unknown in other medieval weapons. The system mattered. The mixture mattered. The secrecy mattered most. The formula was a state secret. Not metaphorically. Artisans were compartmentalized. Knowledge was divided. Production was controlled directly by the imperial court. Written recipes were forbidden. Transmission was oral, selective, and enforced. When craftsmen died, the knowledge narrowed. Byzantine records show repeated efforts to prevent capture. Workshops were moved. Personnel reassigned. In some cases, evacuated entirely. The weapon's effectiveness depended on the enemy never understanding it. Classification was the technology. Speculation ranges widely. Petroleum distillates, quicklime, sulfur, resin. Each explains part of behavior. None fully account for ignition on contact with water, combined with controlled projection. What matters is not the exact recipe, but the operational outcome. Greek fire worked. Repeatedly, reliably, at scale, and then it vanished. By the late Middle Ages, references grow vague. Later empires attempt reconstructions and fail. The siphons disappear. The crews are gone. The training line ends. One court engineer mentioned in imperial correspondence disappears from the record after a failed siege defense. No dismissal. No replacement. He never reappears. Modern chemists have attempted reconstructions. Some mixtures ignite on water. Others burn intensely. None replicate all reported properties simultaneously. Each solution solves one problem and introduces another, which suggests the original was not a single substance, but a system, materials, handling, storage, and delivery working together. This is where the pattern tightens. Like Roman concrete, the performance depended on intentional instability, materials designed to react over time or under specific conditions. Like the Antikythera mechanism, the knowledge was precise but undocumented. And like the lime class in ancient harbor concrete, what looked dangerous or inefficient by modern standards was actually the point. Not impurities. Not accidents. Controlled risk. Greek fire did not fail. It was protected until the system collapsed around it. When the empire weakened, the knowledge didn't transfer. It terminated. And with it, a weapon that history still cannot reproduce with confidence, despite understanding far more chemistry than its creators ever wrote down. Which raises the same uncomfortable possibility again. Some technologies don't disappear because they're inferior. They disappear because they were never meant to spread. Imperial classification level. Sealed. Story 9. The L.Y. Kyrgyz Cup, Roman Empire. 4th century CE. In ordinary light, it looks unremarkable. A Roman glass cup, green, thick, decorated with a hunting scene. For centuries, it was treated as a curiosity, fine craftsmanship, nothing more. Then someone shone a light through it. The color changed. Not slightly. Completely. The glass turned deep red, glowing from within, while remaining green when light reflected off its surface. The effect was immediate, stable, and repeatable. 2 colors. 1 object. No moving parts. This behavior is called dichroism. Today, it is achieved using nanoparticles engineered to precise sizes. In the Lycurgus cup, those particles are gold and silver, suspended within the glass at scales smaller than 100 nanometers. not traces, not contamination. Deliberate inclusion. Modern spectrometry confirms it. The particles are evenly distributed. Their size is controlled tightly enough to manipulate how light scatters and transmits. Change the size slightly and the effect fails. The glass was tuned. Roman glass makers were not supposed to know this. Nanotechnology requires an understanding of material behavior at scales invisible to the naked eye. Yet, the cup performs exactly as designed. Centuries before optics could explain why. Early explanations leaned on accident. A lucky batch. Unintended impurities. But accidents don't repeat precise outcomes. And this wasn't the only example, just the best preserved. Not impurities. Not coincidence. Process. What's missing is a method. No Roman text describes how to suspend metallic nanoparticles in glass reliably. No furnaces survive with clear evidence of controlled particle synthesis. But the result sits in museums, unchanged. When the cup was studied in the 20th century, findings were downplayed. The language softened. Decorative effect replaced engineered property. The implications were bracketed. Because if Roman artisans could tune optical properties intentionally, then material science didn't begin where we say it did. One conservator involved in early optical testing argued for deeper study across similar glassware collections. The proposal stalled. He was reassigned to administrative duties. He never returned to research. Here is where the earlier breadcrumb closes. Like Roman concrete, the key was not purity, but control. Inclusion, not refinement. Lime class strengthen harbors by reacting later. Nanoparticles tune glass by interacting with light itself. Different domains. Same philosophy. Design materials to behave over time or under specific conditions. That philosophy appears too often, too early, to dismiss. Today, the Lycurgus cup is used to teach modern engineers about plasmonic resonance. It performs exactly as textbooks predict once the theory exists. The object didn't change. Only our explanation did. Which leaves one final problem. If this level of control existed in the 4th century, why does it vanish completely afterward? No medieval continuation. No Renaissance refinement. No gradual handoff. Just a single object, doing something it shouldn't, until science catches up and pretends it was always obvious. Particle sizes measured below 100 nanometers. Story 10. Mechanized automata of South Asia, Indian subcontinent, medieval period. The machines are described, not displayed. They appear in court chronicles, engineering treatises, and travel accounts written centuries apart. Self-moving figures. Mechanical attendants. Water-driven devices that respond to input and change behavior. Not toys. Not metaphors. Functional systems explained in technical language. Valves. Cams. Feedback. One text describes an automaton servant that pours water, pauses when the vessel is full, then resets itself. Another outlines a sequence control mechanism driven by rotating drums and pegs, an early form of programming. The terminology is practical, not poetic. Action. Response. Reset. These were not myths for entertainment. They were instructions. Scholars initially treated the descriptions as exaggeration, symbolic storytelling, courtly fantasy. But the details resisted that framing. Component lists were specific. Failure modes were noted. Maintenance was discussed. Fiction doesn't warn about wear. Several passages align closely with mechanical principles known much later: binary states, sequential logic, hydraulic regulation. The systems described resemble the gearing logic of the Antikythera mechanism. Different culture, same mechanical grammar. That similarity matters, because it suggests convergence not of ideas, but of capability. No physical automata from this tradition survived intact, with decays. Leather rots. Metal is recycled. What remains is text, untranslated for centuries, scattered across languages, often ignored because no artifacts accompanied them. When partial translations began in the 19th and early 20th centuries, interest was brief. Colonial scholarship prioritized classification over reconstruction. The machines were categorized as curiosities and moved on from. The text stayed unread. One modern engineer attempted to build a working model based on a single manuscript. The design functioned, briefly. The project lost funding before refinement. He dismantled the prototype himself. This is a final hinge. From Antikythera to Byzantine siphons, from Roman materials to Andean stone, the pattern repeats. Advanced systems appear with no visible developmental trail. They work. They are used. They are not preserved. Here, the loss is total. Only descriptions remain, which suggests something more fragile than metal or stone was at work. A tradition dependent on apprenticeship, on embodied knowledge, on transmission without redundancy. When that chain breaks, nothing replaces it. And when historians look back, they see gaps and assume ignorance instead of loss. These automata do not prove a forgotten golden age. They prove something narrower and more unsettling, that human ingenuity has reached sophisticated states before and failed to carry them forward. Not because the machines didn't work, but because the systems that sustained them collapsed. Which leaves us where this dossier began, facing a past that doesn't behave as expected, and a present built on the assumption that progress only moves one way. If that assumption is wrong, then the question is no longer what ancient people could do. It's what we've already forgotten. Cross-text mechanical concordance dated across 4 centuries.